Hola, ¿qué tal? Bienvenidos de nuevo. Vamos a seguir nuestra conversación con los expertos del día de hoy. Professor Mundell, I have been informed that you are an expert in gamma ray bursts. Is that true?
It's true.
It's true. Recently was discovered an interesting phenomenon called the radio burst. What is the connection between these two phenomena?
So one connection is the way we discover things in science. Gamma ray bursts were discovered by military satellites in the late 1960s, early 70s, and they were actually monitoring the Earth for signals of violations of the nuclear test ban treaty of the day. And the way those violations would be detected would be instantaneous flashes of high-energy gamma rays in the detectors. And the scientists around the time found these flashes, but very quickly, fortunately, realized that they weren't terrestrial, they were actually coming from space. And that was really where the birth of that field then came. One of the challenges that astrophysicists had, though, was that the accuracy of the positions from where these flashes occurred on the sky was very inaccurate. So, of course, if you say to anybody who has a telescope, go out into the back garden, you have maybe a second to look up in the sky with your telescope and find a visible counterpart to one of these flashes, and I won't be able to tell you really where in the sky it is. Go look. That's almost impossible. So the field languished for about 40 years until we had a new generation of technology, a high-energy X-ray satellite that was able to pinpoint the X-ray light from these new black holes. Actually, we now then for black holes formed in the distant universe. And so technology really marches on, particularly in astrophysics. You need to be able to localize something in the sky. We need to be able to capture visible light, and then we do what's called measure a spectrum. And this is actually looking at the light cut into tiny little fragments across the wavelength regime to try to measure the distance to the object, and then we can figure out where it is, if it's in our own atmosphere, if it's in the Milky Way, if it's in the distant cosmos. Fast radio bursts, which you talk about, were discovered again serendipitously back in 1997. Radio astronomers who were studying dense neutron stars, so these are the endpoints of stars that collapse. The material is very, very dense, so one sugar cube of neutron star material would weigh about the same as a medium-sized mountain, all crushed together in this dense heart of a star. They spin very quickly, they have magnetic fields, and when their beam passes the Earth, you get a blip in the radio spectrum. And so the scientists had this very special equipment that was measuring, looking for these pulsars. And a scientist called Duncan Lorimer, actually at Jodrell Bank Observatory using the Parkes radio telescope in Australia, found what would be called a bit like an atmospheric whistler. So it was a very short-lived flash of very bright radio waves that just lasted for a fraction of a second. So of course it was very difficult, and as yet we haven't yet been able to find the simultaneous counterparts to these at any other parts of the electromagnetic spectrum. And what the radio astronomers were able to do with that signal, they were actually able to measure or infer a distance, because these radio waves come through material and it changes the nature of the signal. And so with some guesses and some theory, they were able to figure out the length of the path through which these radio waves have come. Many more have been discovered, and in fact new detectors that are now being put on radio telescopes around the world are starting to find many more of these things. And the idea is that we think they exist either in very dense regions in our Milky Way. Some people think that. Most astronomers are convinced that they actually lie at cosmological distances. So we don't know what produces them. There have been there have been some suggestions they're alien civilizations. I think most of us think that there's no evidence for that yet. So I think most of my colleagues are saying it's not aliens. I'm still saying it's not aliens. We have no scientific evidence for that. It's a nice idea. But yeah, probably very, very energetic processes. So the race is on. We're all trying to use our robotic telescopes around the world to catch other signatures of these fast radio bursts. So it's a very exciting time to be in astrophysics.
It sounds great. Yeah. Professor Kosterlitz, you are worldwide known because of a sentence called exotic matter.
Sorry?
Exotic matter.
Okay, yeah.
Tell me a little bit about that. Think that now I'm a kid of 6 years old. Try to think of that and what we can do with that. Well, 7 if you want.
I don't think there's much you can do with it.
But I can try to understand.
Because, sorry to go a bit technical here, but I think I have to. The point is that I'm interested in what goes on in two spatial dimensions.
Okay.
I imagine myself living in a two-dimensional world. In this case, you ask yourself what sort of structures can exist in this two-dimensional world. You know, a crystal, for example, in 3 dimensions is as, you know, you have a set of atoms on some 3-dimensional lattice. In 2 dimensions, these the 2-dimensional crystal would form some regular pattern, you know, in flatland. And you can ask about the properties of this 2-dimensional crystal. Well, the first property is that the conventional idea of a crystal is that if I know where one atom is, I know where all the others are, because there's a nice regular periodic pattern, and the atoms are, you know, are in this nice periodic pattern. So you know where one particle is, you know where all the others are. In 2 dimensions, that is only half true because of thermal fluctuations, in that because the displacement from the ideal position of the atom, if you ask the question, okay, I've got 2 atoms which in the ideal crystal would be some distance apart,
Okay.
what will they be, where will they be when you've got thermal, you know, at finite temperature, thermal effects? And you discover that the displacement from its zero temperature position, or equilibrium position if you wish, grows, increases logarithmically with the size of the system, so that with a large system, the displacement of the atom from its equilibrium position is basically infinite. So at which point you say, okay, crystal doesn't exist in 2 dimensions. Then you look at it a bit further and you discover that some of the aspects of a crystal will still work in 2 dimensions, as for example, the crystal axis. You know, if you have a triangular crystal, you'll have 6 crystal axes, 60 degrees apart, and you can ask, what about the orientation of these crystal axes, you know, due to thermal fluctuation? And you find that in 3 dimensions, that would be basically fixed. I mean, you know, no deviation due to temperature. But in 2 dimensions, the deviations are large, and you get these logarithmic divergences again. So again, you'd say the crystal doesn't really exist. But it's still this structure, although you can't really call it a crystal, still has all the other properties of a crystal, like it's got finite elastic constants, you know, as in, you know, rigidity and compressibility, just like a normal crystal. It's still perfectly well defined and you know, non-zero, so that you could say that these are the defining characteristics of a crystal.
Okay.
So, as I said, it depends on what property of the material you look at in 2 dimensions. In some aspects, it looks just like a 3-dimensional version. In other aspects, it looks very different. And so it's an interesting world.
It is absolutely interesting. This is the type of things that someone can make a Nobel Prize.
Well, yeah, but it's an interesting thing it's an interesting system to sort of try to figure out what's going on.
Okay. So I think all of us are very aware about how important it is to the governments know that science is important. But for us, it's also important to, I don't know, struggle a little bit with them in order to make them know that to put some funds on that. Professor, you are a counselor in United Kingdom. How do you think that we should do? We should try to push our government, our president, and all the people here in order to put some more money in this type of researches?
So in my experience, actually, both in the UK and Chile, there's there's real recognition in our governments that science and investment in science and technology and then the pull through into innovation is actually critically important. In the UK, our Prime Minister announced a new industry strategy. She actually made that announcement at one of our national labs. She's since been back and made other announcements, actually at Jodrell Bank Observatory, where I did my PhD, with the giant radio telescope behind her. And so I'm very heartened by that recognition at the heart of government that not only is scientific research and those pursuits important, but in my role as scientific advisor, that actually bringing the best science-based evidence into policy making and to inform policy making is very important. You know, politics actually is dealt with by politicians, but that recognition that making sure that decisions are challenged and informed by the best scientific evidence is one of the roles that I play there. And my visit to Chile, apart from having the pleasure to speak at the Futures Congress, is also that involvement with ministers here in Chile to continue to build really strong collaborations that have been there for some time between our two countries, where academics and researchers work at that very you know, scientist to scientist level, but actually making sure that the structures are in place to enable scientists to continue to do the best work that they can for the benefit of their countries.
Thanks. And you, Professor, what do you think, what kind of advice you can give us in order to make our politics fall in love with science?
Well, you know, I was going to ask Carol a question, but don't you think the fundamental problem is the education system? Because most of the teachers don't understand science, so they can't teach it.
Yeah, I think it's really important sort of what you define as science. So there's obviously the fundamentals of the frontiers of scientific research that you might think in your universities and your research institutes. I think how we feed back, as we've been talking about in this conversation, that passion, that you ignite that or you continue to support that in children. I think that's really important. Their families also, you know, helping parents and families understand the opportunities that there are for children through their careers. And I think also the education system to enable and support, not necessarily to educate everybody to become scientists, but actually to help people become scientifically literate. Because as I was saying before, when scientists do their cutting edge research, those conversations about how we use that research has to be held in society, whether that's in your governments or whether that's in your communities.
Let me give you a parallel. I mean, every child at school is expected to learn a language. Another language, like, you know, most French or whatever. Why shouldn't every kid be expected to learn some basic science?
So I think children
make it just part of the essential, the required curriculum.
So my understanding in many countries that is the case. I think one of the problems I've seen with working with schools is to how to keep the real passion. There's something about saying it's compulsory that you do this. It's very different saying well, you can do this and love it while you're doing it. So I think it's both of those, actually supporting teachers so that they have the toolkits that gives them the confidence to basically engage with exciting science.
Well, of course, that's essential,
yeah.
that the teachers are understand enough about the science that they're able to teach it
we should have
with enthusiasm.
This conversation for the homework in order to make our politics fall in love with this. I would like to say thank you to both of you. Muchas gracias a todos ustedes por escuchar esta conversación. Gracias.